Welcome to this FP Complete webinar. As you can see from the beautiful slides that we've got on the screen, today we're going to be talking about async exception handling in Haskell. My name is Michael Snoyman, VP of Engineering here at FP Complete. Yeah, let's roll. Many languages have some kind of exceptions, but most languages out there have the kinds of exceptions that in Haskell we would call synchronous exceptions. We're not going to get into all of the different trade-offs with exceptions today. I'm just going to say that exceptions have a little bit of a double-edged sword to them. You can argue that exceptions make it easier to write correct code. You don't have to worry about checking the return code of every single possible function that you're going to call. Instead, you can allow the exception mechanism to allow things to bubble up. But a downside is that this exception mechanism can lead to a lack of resource cleanup. You can forget to clean up after yourself if you don't handle things correctly with exceptions. GHC Haskell has this thing called asynchronous exceptions as well, in addition to these synchronous exceptions, which essentially just bump everything up a whole nother level with extra features and extra things you have to be careful of. On a side point, I said GHC Haskell because asynchronous exceptions are a feature of the GHC runtime. For the most part in this talk, I'm probably going to interchange between saying GHC Haskell and Haskell. Everything applies only to GHC's version of Haskell. So the way we're going to talk about things today, we are going to build things from the ground up. We got to understand exceptions if we're going to understand asynchronous exceptions. So what are we going to cover today? We are going to be looking at the different types of exceptions that exist and trying to define them. We're going to talk about what it means to have correct synchronous exception handling. We're also going to talk about pure code and bottom values, undefined, those kinds of concepts, and see how that plays in, because there's a lot of confusion about bottom values versus asynchronous exceptions. We'll get into asynchronous exceptions themselves, this concept of masking and uninterruptible masking, and we're going to tie things off by talking about helper libraries that can make this a whole lot easier, as well as look at a bunch of complex examples. Yeah. Actually, could people just drop into the chat and make sure that everything is still working? Okay, so you guys need a little, okay, I'll make sure to give a little bit of a pause. Thank you. Okay, cool. So let's keep going. So we're going to get started with some other ground. One other thing that I want to give people a warning about is that async exceptions are a tricky concept. There's no doubt about that. And that's why we, as people know about me, I spend a lot of time talking about them and thinking about them, and lots of other people in the Haskell world do the same. However, you should keep in mind that they're not nearly as terrifying as they're made out to be. And just like anything, once there's a certain level of lore and confusion and fear that builds up around things, they become much worse. Prime example being monads. Hold on. Yeah, if you guys want a link to the, 1 second, I will give you guys a link to the slide deck so you can follow along yourselves. Okay. You should be able to follow that now. So the point is, don't think of async exceptions as this horrible, terrifying thing you're going to have to deal with. For the most part, we'll get to those helper libraries at the end. You'll be able to, for most of your Haskell coding, not worry about async exceptions, though it's obviously very important to be able to understand what's going on underneath the surface. One final topic. Are exceptions good or bad? And the answer is we don't care today. We're not making any kind of value judgments about whether async or synchronous exceptions are a good or bad thing. I know that there's been plenty of debate about this, also comparing it to alternatives like the except T transformer. It's not our topic today. The point is that if you're using GHC, you're using Haskell today, these kinds of runtime exceptions, synchronous and asynchronous, are a reality that you're going to have to deal with. So it doesn't matter how you feel about it, you're going to need to learn how to play around with this. All right, so now let's talk about a little bit of a teaser. By the way, people who are using the slide deck, you'll want to hit space to proceed to the next one, because this slide deck is actually two-dimensional. So spacebar will let you go down the columns correctly. Shift space also goes back. Yay reveal.js. Okay, So this is a little bit of a teaser. I've written this function called bad race. For those of you who aren't familiar with it, race is a function from the async package, and race allows you to run two different computations at once and will automatically kill the slower one and return the result of the faster one. I've written a bad implementation here. It's got at least two major problems with it. It's probably got many more. It's also not, terribly efficient either, but that's not our topic for today. By the end of this talk, my hope is that you will be able to look at this and identify why it is that this is problematic, and we will come back to it later on. So motivating example, I already mentioned that when it comes to exceptions, one of the big things that we have to deal with is proper resource handling. And really talking about scarce resources. You'll see why I say scarce in a second. File handling is a primary example. File handling is a relatively simple topic, but file descriptors are a scarce resource in a program. When you deal with a file, you have to open the file, and opening up that file may fail, it may succeed. You have to interact with that file, which also may fail or may succeed. And then, regardless of anything having failed in the interim, you have to be able to close it. If you don't do this, then you do not have safe code. You do not have code that cleans up after itself. We're going to start off by playing around with this example in a theoretical Haskell that has no runtime exceptions. And we're going to build things up from there. The detour, though, that we're going to hit first is talking about pure code. Pure code is not a place where you really get to deal with exceptions. There's no way to catch exceptions in pure code. As you'll see later, the try function, which we're going to be playing around with, lives in I/O. And this actually makes sense. If you think about my definition that we're talking about cleaning up scarce resources, you can't actually acquire scarce resources in pure code. So now let's fight back and look at the exceptions to the comment that I just made. Well, you can't catch from pure code, but you can actually throw exceptions from pure code. We'll get to that later, and we'll see why that's not really a problem. You can technically use unsafe perform IO. I know someone's going to bring that one up. So technically, you can do unsafe perform IO. Again, we're not talking about that case today. You can allocate memory from inside pure code. And this is where that definition of scarce resources is important. We're using a garbage collected language, and in a garbage collected language, our definition of scarce means we don't care if we use a lot of memory. We don't care if memory gets cleaned up in a slightly delayed manner. File descriptors, by contrast, we want to clean up immediately. So that's the difference there. And technically speaking, you can, once again, using unsafe perform IO, actually catch exceptions in pure code. But again, that's not something we're too terribly interested in. The outcome from everything that I'm trying to point out here is that pure code is not an important topic that we're going to be looking at here. Almost everything we're going to be looking at is going to live inside I/O. I/O itself, not transformers. We will talk about transformers a little bit. And this is by design. This is the land in which exceptions actually matter. So now we're on the land of no exceptions. Haskell, so hold on, it looks like. So is everyone able to now catch up to the land without exceptions? Okay, we look good. Okay, I've put together an implementation of a function which is going to interact with a file in some theoretical version of Haskell that has no runtime exceptions. Since there are no exceptions, we have to represent all possible failures directly at the type level. So as you can see, this open file function is returning a value, IO, and then an either value, either an IO exception or the handle itself. The hclose function, by the way, if I get distracted, I'm just checking out everyone's comments and making sure that everything is still working. I understand that there are some problems with the video not updating. Is that any better? Are people able to see that now? Okay. Okay, got it. Looks like I figured out the trick. All right, now I know how to get everything updated. So, open file. Yeah, I will go ahead and make a comment when we have to switch slides. Apologies for not doing that till now. All right, so on this land of no exceptions, hclose, we're just returning IO of unit because we know that it doesn't actually fail in any way. Uses file handle, this is some theoretical function we've written up, which is going to somehow interact with the file. It's either going to be pulling out some data, it's going to be parsing it, doing something with it. We don't really care too much right now. We're able to tie all of this together, and we're able to write this myfunc. And in myfunc, we're able to open the file, get an either handle, and then we're able to pattern match on it. If it's a left value, we simply propagate that left value outside. If we actually got a handle, we use that handle, we immediately close, and then we return our error value. And in a land without runtime exceptions, this is perfectly safe code. We are guaranteed that the file is going to get closed before we moved on. And this is perfect. But now, let's get into something which is more realistic of actual Haskell code and look at a land that has synchronous exceptions. And we're going to add two new primitives. And some people who are out there are going to point out that catch is actually the primitive, not try, but try is easier to talk about for the examples we're going to deal with today. So we're just going to pretend like that's the most primitive thing in the Haskell world. So we've got these two functions. We've got throw.io, which is going to cause an exception to bubble up. And this is very similar to throw or raise in basically any other programming language that exists today. And we've got try, which is going to take an action, and it's going to intercept any exception that was bubbling up. And this is what we call synchronous exceptions. And I'm going to define them as exceptions which are generated directly from the IO actions that you're calling right now. Now that definition may seem a little absurd. Of course, it's being generated by the thing you're doing right now. When we get to asynchronous exceptions, then it'll make much more sense why we needed to have that specific definition. All right, so now we've got this land of synchronous exceptions, and now we have a world in which any IO action may cause an exception to be thrown and the code to stop progressing. So let's see how we're going to rewrite our function. Well, the first thing we can point out is that the code is shorter. Significantly shorter, because we no longer have to worry about openFile returning an either value. We know for a fact that openFile is going to be returning an either value. We also know that hclose, just like before, it's going to return an IO of unit. So one downside you can point out about this exception world is you can't actually tell that hclose is not going to throw an exception. Unfortunately, that's just the reality of the way that we have things implemented in Haskell today. Looking at a type, you no longer know whether it can fail or not. And you have to assume, therefore, that basically everything can fail. And again, uses file handle just like openFile, doesn't need to return an either value anymore. myfunc is now pretty short. We open the file, and we get a handle. We use the file handle, we close the file handle, and we return the result. The problem is, what happens if uses file handle throws an exception? If it throws an exception, then hclose is never going to get called. Everything is going to get interrupted before then. So this is not exception-safe code anymore. We need to do something to fix that. Fixing it is pretty easy. We use try and throw. We don't need to worry about putting try around the open file call. If open file fails, it means we didn't open up the file at all. If we didn't open up the file at all, there's nothing that we need to bother cleaning up, which is great. If uses file handle causes any kind of an exception, we still need to make sure that we clean up after ourselves. So we wrap that with try, and now we know for a fact that there's no exception which is going to bubble up and interrupt our function. We capture an either result, we then immediately close the file handle, and then we pattern match on the result value and either rethrow the exception with throw.io, let it bubble up even further, or we return the successful result. And in a world of only synchronous exceptions, this code is perfectly exception safe. Now, obviously, there's a caveat there because as the title of this talk kind of implies, we have asynchronous exceptions also. So don't run off and use this in your Haskell code. You got to wait until the end of the talk to actually see what's safe. But this, in our theoretical Haskell, is safe. Now, of course, having to think about that every single time, remembering to open the file, remembering to do the catching and everything else, that's very error prone. So one of the things we like to do in Haskell is capture this pattern. We call it the bracket pattern. You'll see later that we have a function called bracket. Actually, I'm not sure if we talk about bracket later on. I don't remember right now. But we call it the bracket pattern. And the idea is that we bundle up together the action of acquiring the resource, this time opening a file, and cleaning up the resource, in this case, closing the file. And that way, it's impossible to misuse with file. It's impossible to use the function with file in a way which is going to cause a resource leak. So we've just slightly altered things. You have to be very careful when writing with file itself. But now that you've written with file, you can write a function like myfunc and not worry too terribly if you are doing anything exception unsafe. So the general principle that you should follow is avoid using functions which only allocate or clean up. You should use functions which do both. There will be times when you're going to have to go a little bit lower level, but if you can avoid it, avoid it. And one of the questions, an advanced question, which we're not going to get to here, but feel free to follow up with me afterwards about, well, the hclose, we already said this thing isn't going to throw an exception. But what would happen here if hclose did throw an exception? What would happen in general if our cleanup code throws an exception? How does that throw a wrench into our operations? We're not going to worry about that right now. It's actually not going to come up in the rest of this talk, but it's an interesting thing to think about. Okay. The type signatures that I gave before assumed that the types we were dealing with were IO exception, that all exceptions that could be thrown were IO exceptions. Anyone who's worked with the exceptions API in Haskell at all knows that it's not actually that simple. And we have basically an OO style extensible hierarchy of exceptions, very similar, and I think, if I'm not mistaken, based on what we've got in Java. So don't be disgusted, but yeah, we stole something from Java, it seems. The way things work is we have this data type called SUMException. And SUMException, using object-oriented terminology, SUMException would be the superclass of all possible exceptions. So all exceptions in the hierarchy must be a child class of SUMException. Now, obviously, we don't have that kind of extensibility in Haskell. We have different mechanisms. So the way we get this to be implemented is with this type class called exception, which allows you to convert to a SUMException value, and then try to convert back from a SUMException value to your local exception type. And if this seems a little bit wonky and you're not familiar with the typeable type class, this may seem a little bit weird, but it's an integral part of how we're going to end up dealing with async exceptions. You only have to know at a high level that we're looking at this kind of hierarchy of exceptions. Now, the more general version of our throw IO and try functions simply replace the concrete IO exception type with a type variable and an exception constraint, as you can see down there. I can give you an example here of what it looks like to have your own custom exception type. This is saying I've defined a new exception type, invalid input, and I would like to say that in order to convert it to an exception, I just wrap it up with SUMException, meaning it is a direct child of the SUMException data type in object-oriented terminology, and then we're going to use cast to convert back from from the SUMException to our concrete data type that we've defined. And these actually turn out to be the default implementation. So if you want to write your own exception type, you can actually just write instance exception invalid input, or whatever your data type name is. We can also do hierarchies of exceptions. So here we've defined this myAppException, which has two different data constructors, invalid input, the one we had before, and something else. And here we've defined a subexception data type, which has a network failure data constructor. And as you can see, what we're doing here is, in order to convert it into a SUMException, we first wrap it up in that something else data constructor and then pass it up. So you can see that this is wrapping in the parent class. The parent class is no longer some exception. The parent class is this my app exception. And this allows us to create hierarchies of exceptions, which later on we're going to see how we use that to distinguish asynchronous exceptions from synchronous exceptions. So if that somewhat went over your head, don't worry about it. It is using some obscure pieces of Haskell. It's not terribly important to understand the mechanism right now. All right, another question. I defined this thing called throw IO. Why isn't it just called throw, like most other languages would call it? Well, it turns out that we have a function called throw that also exists. And you'll notice that it is returning a value A. It's not returning anything in IO. Contrary to popular belief, contrary to some comments that pop up pretty often, these are not asynchronous exceptions. I like to call them impure exceptions because they break purity of code. This is also where a function like the error function or undefined, this is how they work under the surface by using the throw function or an equivalent of the throw function. And what they do is they create bottom values. And when you evaluate these values, then you're going to end up causing an exception to get thrown. So how can you do this? Well, you could use the throw function directly. You could use a function that calls it, like error. You could use partial functions like head, and these also generate these runtime exceptions. Incomplete pattern matches. If you forget a case, then GHC will automatically fill in those missing cases with exceptions. And also, you can create infinite loops in your pure code. GHC's runtime system may or may not be able to detect that you've gone ahead and created an infinite loop and then cause an exception to be thrown. So, yeah, sorry, everyone. Creating impure exceptions is the slide we're up to. I know I just realized I've forgotten to give everyone updates. So we're going to move on to the next slide. So I'm sure I'm preaching to the choir here. I'm sure everyone here hates impure code and partiality. So we're not passing judgment here, but I'm passing judgment. Try to avoid these things if you can at all do it. Okay, next slide, challenge. What's the output? So I've gone ahead and I've created this exception type called dummy. And I have a helper function printer, which is going to print an IO value of either dummy or a unit value. And now I have 5 different ways of throwing this dummy value. What's going to be the output for each one of these? So we're going to move on to the next slide, which is case 1, where we use throw IO. And in this case, throw IO is going to cause a runtime exception to be thrown. Try is then going to immediately catch that runtime exception. And then we're going to pass that on to printer. So we're able to catch this and turn it into a concrete value, left dummy, and we print that out. Moving on to case 2, now we're using throw instead of throw IO. Because of the way we're using it here, throw is essentially equivalent to throw IO. Since it's generating an IO action, that's the type that it's generating, as soon as we try to run that IO action, it will cause that exception to be thrown, and therefore try is going to be able to catch that immediately. So we'll end up with the same result. Moving on to case 3, the next slide, we're now going to use throw dummy, which is going to create a value of type unit. And then we're going to use the evaluate function, which is going to force evaluation inside IO. Now that we forced evaluation of it, that's going to cause the exception to be thrown. And once again, try is going to be able to catch it. Moving on to the next slide, case 4. Instead of using evaluate, we're going to use return and $bang. People who aren't familiar with it, $bang uses a function called seek under the surface, and seek, S-E-Q, is used to force evaluation. Slightly differently from the evaluate function. We're not too terribly interested today in the difference between seek and evaluate, but yet again, we get this left dummy value. So who can guess? Who thinks that case 5 is going to be the same thing yet again? All right, so moving on to case 5, here we have something slightly different. In this case, when we do throw dummy, we are going to be generating a value of type unit, which is which when evaluated will throw an exception. The next thing we do though is we wrap that up using return in an IO action. At this point, we have not actually created, when we run this IO action, we're not actually going to be forcing that value at all. We're not going to cause anything to get thrown. Therefore, when we run try on it, try isn't going to catch any kind of an exception. We are then going to get to this printer function. The printer function is going to see a write value, and inside that write value is going to be a thunk, which, when evaluated, that evaluated thunk is going to throw an exception. So this thing is actually going to cause your program to crash because the exception is going to pop up at the wrong time. And this is the beauty and the wonder of impure exceptions, and it's why you should try to avoid them whenever possible. So moving on to the next slide, what's the upshot of all of this? Why did I go into this seeming tangent? I want to point something out. Firstly, don't use throw or error whenever possible. If you're going to be using runtime exceptions, throw IO is a much better choice because of this. The other thing is pure exceptions seem to pop up at random, and that's why they have this reputation of being related to asynchronous exceptions, because they pop up at random. However, in every single case that I showed you, including that exception, case 5, which was the exception to the rule, I'm probably going to make that pun unintentionally many times. I apologize in advance. Even in that case 5, the trigger for causing that exception to get thrown is always local to what we're doing right now. It is always the fact that we're forcing evaluation of that thunk in IO. So therefore, by our definition that we gave before, impure exceptions are synchronous exceptions because they're coming out of our current execution. That means that we get to simplify. If you've read some of my previous material on this, I've talked about the 3 kinds of exceptions: synchronous, impure exceptions, and async exceptions. For our purposes today, we're going to get to lump in impure exceptions with synchronous exceptions, because even though they get generated from pure code instead of from IO code, the way that they get handled and the way that they affect resource cleanup, which is the main thing we care about today, since that's what we care about today, we just get to lump them in together. The other thing is impure exceptions are usually irrelevant for our cleanup. So in this case, I'm just showing the same with file function that we had before. Let's say, for the sake of argument, that this inner function returned a bottom value. It used the throw function and created a thunk, which when evaluated is going to cause an exception to be thrown. Does it break our with file function? The answer is no. It does not break the with file function at all. The reason is, if you look carefully, there's no point at which we force the evaluation of the result value that the computation generates. And therefore, everything is fine. So we've gone ahead and we've talked about a land that has only synchronous exceptions, and things kind of make sense there. Let's try to understand why we would want to make things even more complicated, which, as I mentioned, async exceptions are a complication. So why would we want to do this to ourselves? What extra value are we going to get? So we're going to, so actually I just saw Pavel raised his hand. I haven't, again, this is for people who are on early, this is the first time we're using the software. This is new. Pavel, do you want to drop a question in? I think I can. Oh, it was an accident. Sorry about that. Okay, cool. So let's try to understand why we would want these async exceptions. Let's say we want to write this function called timeout. For people who are familiar with the Haskell ecosystem, timeout is a function that exists with the type signature that I'm giving here. And the idea is you give it an amount of time, you want to give it a function to run, an action to run. You give it the action, and then it'll give you back a maybe value. It'll either be nothing if the timeout got triggered, or the result value. And my question is, without any of the information on async exceptions, without using async exceptions, is there a reason why we would want to use, is there a way that we could write this timeout function? Well, let's take a bad approach first. we're going to pretend that there are no such things as async exceptions still, but instead we're going to add a new feature to our runtime system. And the runtime system now has the ability to arbitrarily kill threads at will. And we're going to say that this built-in primitive is the timeout function. And now I've written this thing. It's going to time out, so this is 1 million or 1 second because it's in microseconds. So I'm going to give this thing 1 second to run. I'm going to use bracket. I'm going to open this file. I'm going to close the file when I'm done, and then I'm going to run something really slow. If things actually work this way, and actually the runtime system simply killed the thread, we would end up in a situation where the cleanup never gets run. hclose would never get called. And this breaks the entirety of safe exception handling that we want to deal with. So if we introduce this to the runtime system, we would essentially break everything we've been working towards until now. So we have to say this is not allowed, we can't do this. Let's instead try to implement a timeout function. It's going to have a slightly different type signature, but we're going to implement one outside of the runtime system. I'm going to define this exception data type, this called timeout. And I'm just defining this helper function. It's called check timeout, and all it is an IO action, and we'll see what it ends up doing. Our timeout function is going to take 2 parameters, just like before. It's going to take the number of microseconds that we want to wait for, and it's going to take the inner function. But instead of just an action, now this action is going to receive this check timeout action that it can use to check whether the timeout has expired already. And we're going to do some magic, not magic, we're going to go ahead and use mvars and IO references. Everything is about mutable variables at this point, because that's the only way we can communicate between these 2 threads. So we're going to use an mvar to hold on to the return value that comes from this thread that we're going to spawn. And we're going to use this IO ref to indicate whether or not the timeout has expired already. This check timeout function, it's actually just an action. It's going to read the current value in expired. And if expired is true, it's going to throw a synchronous exception to indicate that things have timed out. And now this is actually the big trick that we want to understand. We're going to leverage the existing synchronous exception system to cause the death of the thread. That way, all of the safe exception handling code that we've written previously is automatically going to kick in. And in our example previously, it would mean that our file is going to get closed. So that's pretty cool. We're going to fork a thread, which is simply going to wait a certain number of microseconds that were given, and then it's going to indicate that the timeout has expired. And then we're going to fork another thread to run the action provided by the caller of this function, wrapped up in try. And when we finish with running that, if this turned out to be a timeout value that killed it, then we're going to say that we're going to return a nothing value. And if it was something else, then we're going to return the just value. There are some other issues with the implementation. Don't worry about that right now. And then finally, we take mvar, and that will cause us to block and wait until this interaction finishes. And now how do we use it? Well, this is pretty straightforward. We're going to do an allocate. We're going to do a cleanup. And now I'm going to write this infinite loop, which is going to print a message. Then it's going to check whether the timeout has expired, and then it's going to go to sleep for 1/10 of a second. And sure enough, if I do this, the thread does die relatively quickly. You still have that 1/10 of a second delay. So it turns out that we are able to implement something like timeout without any extra support of asynchronous exceptions. So it's positive. We're reusing the existing exception machinery, so everything's safe. But there are plenty of negatives with this implementation. You can't interrupt pure code. Check timeout is an IO action. There's no way to call an IO action. Again, we're ignoring unsafe functions. But there's no way to call this IO action from inside pure code. And the other thing is you have to remember to call check timeout all over the place. or else timeout is going to break. If you get into some piece of your code and you don't call check timeout, then you've broken the timeout function. And this is a really big problem that you have to take into account. There's also deadlock possibilities in the code that I wrote. So if anyone wants to look at that and try to figure out why there's a deadlock possibility in the code, feel free, ping me about it later. So now we're finally at the point where we can talk about what real asynchronous exceptions are. The definition is async exceptions are exceptions thrown from another thread. Now this is different from synchronous exceptions. The local thread does not cause the exception to be thrown. Instead, it's a message coming from the outside world saying it's time for you to die for some reason. These exceptions bubble up just like the synchronous versions do. They can be caught with try, just like synchronous exceptions, or using catch or any of the other helper functions that do the same thing. The only difference between synchronous and asynchronous exceptions is how they are thrown. So here is fork.io, one of the primitives in Haskell for creating a new thread. It gives you back a thread ID, and throw2 is now going to replace throw.io. And throw2 says, give me a thread that you want to kill, give me the exception you want to kill it with, and I'll kill it for you. So now let's compare to our handwritten timeout. Throw2 is kind of like setting that expired variable to true. It means that the next time someone checks the variable, they'll know that it's time to die. The runtime automatically inserts those calls to check timeout. So now the runtime system is automatically checking for us whether expired has been set to true or not. We're no longer responsible for doing those checks. It also means that we can do that from inside pure code. The runtime system does it for us automatically, so pure code can get interrupted. That means if you have some kind of really long-running CPU computation, that thing can get killed by async exceptions as well, which is really nice. The other thing is, and I want to stress this, the runtime system can detect an async exception at any point, because as far as we've said so far, any point in your program, it could decide, hey, now's a good time to check for an async exception. And this can lead to some new unexpected problems. We're going to go back to our with file. I told you we were going to use this as a nice motivating example. The runtime system now, in a world of async exceptions, has added implicitly these calls to check async. About 4 of them. There may be more, and there are definitely going to be a few more going on inside the inner, but we don't care about that for the moment. So if an async exception gets thrown here before we call open file, everything's fine. We're not going to lose anything because we never open the file. If an async exception gets thrown here after we call hclose, again, we're fine because everything has been cleaned up for us. These two, 2 and 3, are the dangerous ones. This is after we've called open file and before we've called hclose. And therefore, we have a resource leak. And with what we've defined so far, there is no way for us to write a safe version of with file because the runtime system could generate an asynchronous exception at any point. So we're going to introduce a new helper function, mask underscore. And what this does is it temporarily blocks async exceptions. If we simply wrap up our with file function with mask underscore, it completely fixes the resource leak immediately. Essentially, we're returning our code to the state that we were at previously when we only had synchronous exceptions. Unfortunately, this isn't great either, because now the timeout function that we wanted to have, remember, all of this was about the ability to write something like timeout. Timeout cannot kill our with file function, and it can't kill the inner function that the caller provided either. That means that if you're working with a file for 10 minutes, there's no way to time that out. This is definitely a problem. We need some way to restore the previous masking state. We need to get back to being unmasked or whatever we were doing previously. So this is a relatively complicated signature, but what it's saying is I'm going to give you some kind of an action, some kind of a function which will unmask or restore the masking state. And you may hear me, you may be a little bit confused. Why am I talking about restoring a masking state versus unmasking exceptions or unblocking exceptions? We'll get to that in one of the advanced examples at the end, but there is a subtle difference, and that has to do with something called the wormhole problem, which sounds really awesome. So I'm sure people are going to go look up wormholes in Haskell soon. All right. This is how you can use restore. So now we've wrapped up our with file function with mask, and we've captured this restore function. We leave open file completely masked. We have to leave open file completely masked. If we restored asynchronous exceptions here, it would be possible that the asynchronous exceptions would get thrown after we had completed opening up the file, but before we'd exited from the restore. And in that case, we would end up losing the resource. Here, we do use restore. We wrap everything up in try, and then we restore asynchronous exceptions, and then we call inner handler. This is totally safe. Our try here is going to intercept any synchronous or asynchronous exceptions that got thrown inside here, and is going to return it as a left value. We then immediately close the file handle again, and we're guaranteed that the file handle is actually going to get closed. And then down here, we rethrow whatever exception happened, whether it's synchronous, whether it's asynchronous, we don't care, it gets rethrown. And this is perfect, this is what we wanted. We wanted to make sure that hclose got called, and now we know that hclose got called. So sometime I'm going to use the term Pokemon again. So catch them all exceptions. You want to catch every single possible exception. The code that I gave you so far, sorry to tell you I lied to you. It doesn't actually type check. Because when you look at this code, I don't know the type of this exception. And if you remember, the try and throw IO functions were polymorphic on some kind of an exception type class. So instead, we have to give an explicit type signature to say that this exception is of type SomeException. Like I said, and this is why I spent so much time talking about that Java-style hierarchy, SomeException sits at the top of the exception hierarchy. So if you catch a SomeException, it means you've caught all possible exception types. So now we've actually caught all exceptions and then rethrown whichever one of those exceptions we caught. So this is awesome. This works. Our code is safe. However, we're going to catch them all again. We're going to look at this code and see what's going to happen inside of it. So I'm going to call timeout with a 1 second delay. And I'm going to say this inner thread, this interaction, has 1 second to run. I'm then going to thread delay for 2 seconds. So the exception, the timeout exception, is going to trigger right here. But I'm going to catch that exception. And then I'm going to delay for another 2 seconds. And then I'm going to return my value. And I'm going to get the time before and after, and I'm going to print the difference. So everyone take a second to think about this. How long do you think that duration is going to end up being? And what do you think the result value is going to be from running this? Okay. The output is 3 seconds, not 1 second. And the reason is we caught that asynchronous exception. We recovered from that asynchronous exception, and then we delayed again. We defeated timeout. We made timeout useless and incapable of actually causing the change that we wanted in our program. Then, after we defeated timeout, we then exited correctly from the timeout function. The timeout function thinks everything went fine, so it returns a just value instead of what it should return, which is a nothing value, indicating that the timeout was triggered. And inside that just value, we have a left value, which is the timeout exception itself that got thrown. So previously, inside with file, we caught SomeException, and we said we could catch asynchronous exceptions, and that was fine. And here I'm telling you, we caught an asynchronous exception, and it was horrible and terrible and evil. What's the difference between these two cases? And this is the vital distinction, probably the most important thing in this talk to get across, is this difference between recovery and cleanup. The rule is you cannot recover from an asynchronous exception. We have two reasons why we would ever want to catch an exception. One of them is cleanup. And in a cleanup scenario, like with file, we catch the exception, we do something else like hclose, and then we rethrow the exception. Since we're immediately rethrowing the exception, we are not interrupting, we are not preventing something like the timeout function from fulfilling its duty. And this is perfectly safe, and we can do this with asynchronous exceptions. Recovery is the problem. Sometimes, for example, let's say I want to read from a file, and reading from a file may fail because the file doesn't exist. Well, I'd like to recover from that and then use a default value or print a message to the user and then download a config file from a URL or a million other things that I may want to do. All of those are fine for synchronous exceptions. But if I did that with an asynchronous exception, I would prevent the ability from an external thread to kill my thread. And that violates the whole purpose of asynchronous exceptions. So again, the rule is, do not ever recover from an async exception. So that's nice in theory. In practice, how do we tell the difference between a synchronous and an asynchronous exception? Well, as I told you before, there's only one difference between these two, and it's how they're thrown. Whether you use the throw.io function or something similar to it, or if you use the throw.to function, which is for asynchronous exceptions. The problem is that when you catch the exceptions using try or something else, there is no indication as to which of those two functions was used to throw the exception in the first place. And this is a problem. It's not just like there's a library problem here, it's in the runtime system itself. The runtime system maintains none of that information. So there's actually no way to legitimately and 100% know whether an exception was synchronous or asynchronous in nature. There are two techniques that exist for approximating this, and the approximations are very good. The older technique involves forking a thread and running things in a forked thread. That's a much more heavyweight solution, and we're not going to talk about that. Instead, we're going to use the newer technique, which relies on types. And this is why we talked about the exception hierarchy so much. The warning I have to give you is that it is possible to spoof this. You can use the wrong exception types if you try hard. You shouldn't try hard. You should try to make your code work. So don't try to break things. And as you'll see, the helper libraries we're going to get to are going to help out with this significantly. So some async exception. Some async exception again, we're going to go back to talking about things like it's Java, is a child class of some exception. And it's the superclass of all asynchronous exceptions. And using those to exception and from exception things that we were looking at before, we can write a function that checks based on the type of the exception that's been thrown, whether it's an asynchronous or an asynchronous exception. So here we're going to take the arbitrary exception we have. We're going to, it kind of looks a little weird. We're going to cast it up to a some exception. And then from the some exception, we're going to cast it down to a some async exception. If the casting succeeded, then we know it's an async exception. And if the casting failed, then we know that it's a synchronous exception. We're also going to have some wrapper data types to help us. And these things are going to wrap up other exceptions and make them look like they're either synchronous or asynchronous. The details of this are not too terribly important. This is a little bit more interesting. We have a toSync exception helper function. The toSync exception helper function is going to go ahead and take some arbitrary exception. It's going to check if it's an async exception. If it's an async exception, it'll wrap it up inside a sync exception wrapper. And then the opposite goes on with a toAsync exception. And now we're able to replace our throwing functions with safer ones. Throw.io, since this is the synchronous way of throwing things, is going to first convert the exception into a synchronous exception type. If you try to, by mistake or intentionally, whatever the case is, if you try to use an asynchronously typed exception and use it with throw.io, this kind of a replacement thrower will convert it into something that looks synchronous and therefore not break all of the type-based checking that we're looking at. Throw.to does the opposite. It instead converts it into an async exception. And impure throw is the way that I've renamed the throw function, because I think we should be explicit about it being impure. And again, as we mentioned before, this is a synchronous exception, so we convert it into a synchronous exception. And the final thing we're going to replace is the catchers and the cleanup functions. In the case of the recovery functions, which are things like catch, try, and handle, those things are actually going to check if the exception that they're dealing with is an async. If it's an asynchronous exception, it will immediately rethrow it and not allow you to recover. By contrast, a cleanup function like bracket, on exception, or finally is going to rethrow the exception, or rethrow whether it's synchronous or asynchronous, after you've done the cleanup. And this way, you're able to get that distinction between recovery and cleanup based on the types of the exceptions. Here's an example of what the catch function looks like. I've given a simplified version versus the one that actually exists in the unlift.io package, because this one doesn't deal with all the monad transformer stuff. So we're going to run an action, and we're going to use the underline catch mechanism from control.exception, which doesn't know any of the logic about types. And it's going to check if this thing was a synchronous exception, then it's going to run the cleanup, the handler function. And if not, then it's going to immediately rethrow it. So if you want a simple takeaway from this talk, what is it that you should do practically in your code today to make your code async exception safe? Stick to these modified helper functions. You're not going to accidentally recover from async exceptions, which are the most dangerous things, the most common mistake that people make in this kind of code. And you're even able to do Pokemon exception handling. You're even able to say, hey, I want to catch all possible exceptions. We have this function called try any. And normally, if you're used to control.exception, catching something of some exception type seems wrong. It should seem wrong, because that would allow you to catch and recover from asynchronous exceptions. However, since this is based on our safer version of try that rethrows asynchronous exceptions, this is totally safe. And we'll talk about which helper libraries to use in just a little bit. We talked about masking. You understand now why masking is important. Let me also say to you that low-level masking is a complicated topic, and you should avoid using it whenever possible. Instead, you should use the higher-level functions that exist. And the higher-level functions are things like bracket and finally an on exception. Sometimes you're going to need to know about all the details of masking, and therefore we're going to cover the one final complication in the asynchronous exception world, which is uninterruptible masking. I'm warning you guys in advance, this is the most complicated part of asynchronous exceptions. It's an edge that people cut themselves on a lot. Again, I'm going to reiterate, use the helper functions. You can avoid having to think about this 99% of the time if you use the right helper functions. All right. Mask will prevent async exception polling from happening everywhere. Meaning, if you don't turn on masking, then at any point in your code, the runtime may check if an async exception has been thrown. That's the problem. However, there's still something called interruptible actions, an example of which is take mvar. Interruptible actions will still check if an asynchronous exception has been thrown, even inside a masking. This can be very useful for avoiding deadlocks. By the way, most of what I'm putting on this slide is taken directly from the control.exception documentation, where it talks about interruptible actions. If you're interested in this, you should definitely read that section. It explains this very well. I'm going over this more quickly. The problem with having these interruptible actions is that they can also prevent cleanup from running. The trade-off between deadlock prevention and proper cleanup is a complicated issue. If anyone really wants to get into this, I encourage you to check out this GitHub issue, where we went into lots of detail on this. One of the cool things you can do about this interruptible versus uninterruptible is you can use this function uninterruptible mask to upgrade an already masked state to an uninterruptible state. You can't do the same thing going from unmasked to masked because there's no way to guarantee when you exit the masked state that the that the async exception isn't going to be immediately thrown. In the case of interruptible to uninterruptible, you know exactly where the runtime exception could have been thrown. It could only have been thrown in the interruptible action. That sounds a little bit complicated if I'm over your head at this point. Again, go read the docs. They make these things a lot more clear. So what should you take away from this? If you have to use a masking function, think hard about which one you want to use. Whether you need to be worried about the deadlock possibility, whether using an interruptible masking could lead to the possibility of a resource leak. Better yet than all of this, I know I sound like a broken record at this point, use a helper function instead. And here's a fun little trick. Deadlock detection works in GHC for MVARs and STMs out of the box. We have this ability GHC has this ability to notice that no thread could unblock an MVAR or an STM action, a TVAR, and can throw one of these blocked indefinitely exceptions to clean things up. So in this example, I've gone ahead and I've created an empty MVAR, and then I try to take it. There's no other thread that has access to that MVAR. And therefore, GHC will usually be able to detect that this is a deadlock and throw an exception. You can't rely on this always happening. It's possible that GHC won't notice some of these deadlocks, but for the most part, it's pretty good about detecting this kind of thing. So now I've wrapped this up with uninterruptible mask. In this case, the runtime exception doesn't get thrown, or more precisely, it gets thrown, but it doesn't get received, because now take MVAR is no longer going to be able to check if an async exception is available because we've turned on uninterruptible masking. This is what that deadlock looks like. And if we use a normal mask, then this time the async exception is going to be received because take MVAR is an interruptible action, and now it's going to be able to detect that that async exception has been thrown. So this is a perfect example of the difference between interruptible and uninterruptible. And therefore, based on everything I've just said, you would say that deadlock detection is handled via async exceptions. So let's assume for a second that that was an asynchronous exception. And now we're using this try any function, which only catches synchronous exceptions, and then is going to try to recover from the exception and print out the message that it recovered. So what do you think? Will this thing print out looks like I recovered, or will it not? Take a few seconds. We're actually allowed to recover in this case. The blocked indefinitely exceptions, even though they are thrown asynchronously, are treated as if they are synchronous. They type check based on that type-based inference that we talked about before as being synchronous, even though they're technically thrown from another thread. The reason is that it was a local action that caused that exception to be thrown. It was the act of trying to take an MVAR of an empty MVAR or something along those lines. You may be concerned that you're going to break the async exception handling of your system if you ever run into this. The fact is you're perfectly safe going ahead, catching and recovering from these things. So is this confusing? Yes. Is it logical? I'd argue it's logical and it's useful. All right, we're now at the helper library breakdown. There are 3 different libraries that I know of that implement the logic that I've mentioned. Enclosed exceptions is the oldest of these libraries. It's the one based on the older technique I mentioned of forking threads. Since that's not the technique I recommend anymore, I don't recommend that library anymore either, but you'll still see it referenced. Safe exceptions uses the types-based approach, and it uses the exceptions package, which provides the type classes monad catch and monad mask, and bases on top of that. Unlift.io also uses the types-based approach, but it uses the monad unlift.io type class instead. I'm not going to get into this topic of monad transformers now. I've included a link to a YouTube video. If you go to my webpage, snoyman.com, you'll see that one of my recent talks, the talk at Lambda World, was about this topic. You can watch the talk or you can read the slides. My recommendation these days is to stick to monad unlift.io and therefore the unlift.io package. So go ahead and check that out if you're interested. If you pull in unlift.io.exception, then you will simply get the behavior of everything that we've talked about until now with the modified throw, catch, and recover functions. So now, we're going to summarize. We're going to go on to some examples. I know that we're past the hour. If people want to leave after the slide and watch the recording, that's cool. We're going to continue with the examples anyway, but this is kind of tying it all together now. If something must happen, you need to use a masking function in order to prevent an asynchronous exception from preventing it from happening. That's what we saw with file. Next, if you catch an asynchronous exception, you must throw it as soon as possible. Again, we saw that with the with file example. We tried to catch, we used try in order to catch a synchronous or asynchronous exception. We cleaned up, we closed our file handle, and then we immediately rethrew the exception. A corollary to this is you should not have long cleanup code. If you have cleanup code that could take a long time, you will get back into that situation of breaking a function like timeout, because timeout will no longer be able to guarantee in any way that your code is going to stop running in a fixed amount of time. So make your cleanup code as short as possible, and we'll see an example of that. And finally, you should minimize the amount of time spent in the masked state. This is the same kind of idea yet again. We don't want to mask too much of our code. If we mask too much of our code, functions like timeout are not going to be able to do their job. All right. Using the right libraries, most of this will be implemented for you. You don't have to, you can avoid masking in most cases and use the pre-built functions. If you have to acquire a resource, use a function that does the resource acquisition and cleanup for you. If that doesn't exist, use a function like bracket that has the correct synchronous and asynchronous cleanup logic built in. And only in the most extreme of circumstances, actually use the low-level masking functions in order to do this stuff. Okay, if you're able to do all of that, you're going to be safe. So onward. Again, if people need to drop off, I know we're past the hour. I won't be offended, but if you want to see some cool examples, I happen to think they're fun. All right, who likes this code? We're going to create a channel. We're going to now use the race function, which is going to run 2 threads at the same time. And one of these threads is going to write messages into the channel. The messages are just going to be the numbers 1 through 10. And the other thread is going to loop infinitely, reading values from the channel and printing them. And then I'm just going to simulate some I/O latency and have them delay for 1/10 of a second between each write, each print. So we're using asynchronous exceptions here as a control flow mechanism. There's no way for this thread to ever die on its own. It must be killed from the outside. Sounds kind of nice. Sounds like a nice usage of asynchronous exceptions. However, this is totally broken, because when this function finishes, this thread is still going to be running. It won't have gone through all of the messages in the channel, and now some of those messages in the channel will end up just getting dropped on the floor. The rule here is avoid async exceptions if you can, which might sound strange in a talk entirely about asynchronous exceptions and how they're so cool and useful. The answer is they're cool and useful for a very limited amount of things. Don't use them to deal with control flow. Don't use them as a mechanism for passing messages that could be passed otherwise. Instead, it's much better to use a mechanism like this. I'm using the stmchans package, which is very cool, and provides us with closable queues, closable channels, also a few other things. Again, we're going to have one channel, one thread, which simply writes the messages 1 through 10 to the channel. And then finally, notice I'm using finally myself to make sure that things actually happen. Finally, it's going to close that queue. And now I'm going to write a loop. This is no longer an infinite loop. This is a loop which is going to try to read a value off the channel. If the channel is empty, if it's done, then we're going to exit. So we're no longer relying on the asynchronous exceptions to kill us here. Instead, we're implementing proper control flow ourselves. Otherwise, we're going to do the same thing before. We're going to print the message. We're going to simulate our delay with a tenth of a second, and then we're going to loop again. All right, we sent off an email challenge. And I wanted to ask everyone, is this good or is this bad code? So we're using bracket. We're opening and closing a connection. Once we have the connection, we're using bracket again to send a hello at the beginning, send a goodbye message at the end, and then we're having a conversation. However, you could think of this as an HTTP connection or anything else. It doesn't really matter. So is this good or is this bad? It's bad. Using bracket for opening and closing the connection is very good. Using bracket for sending goodbye is a problem. If you remember, I said earlier that you should not have long goodbyes. If you have long goodbyes, if you have long cleanup actions, then you're going to end up in a situation where timeout doesn't work correctly. You may argue, but wait a second, my network protocol demands that I send that goodbye message at the end. If you do, you have a broken network protocol, because there's no way you can ever guarantee that your process is actually going to be able to respond with a goodbye. Your process could get a sig kill, and there's no way to recover from that. Your machine could die, it could explode. You could have a network disconnection. Any of those kinds of things could happen. So therefore, this is not the right way to write your code. Instead, this is what I would recommend, which seems perhaps counterintuitive for me to say don't write exception-safe code for the goodbye, but that's exactly the right thing to do, because sending this network message could take an inordinate amount of time while you're trying to clean up. There are probably some exceptions to this rule out there. There are probably some cases where you're going to say, no, but I really know that it's more important to send this message. Fine, there might be corner cases, but as a general rule, this is the right way to look at things. All right, second email challenge. This is an implementation of bracket. And I'm going to say it again. Don't write your own bracket. Use the existing bracket. There's no good reason to be implementing these kinds of complicated functions. So go ahead and take a look at this, and then we're going to see, was this a good implementation or is this a bad implementation? So the solution, it's mostly good. So we mask the exception. I'm actually going to jump back to the code itself and look at this slide email challenge too. So we've gone ahead and we've masked this entire block. That's absolutely necessary. That's a good thing, because otherwise we could have async exceptions popping up before we're able to do our cleanup. We get this restore. We don't use restore on the before function. Again, if we used restore on the before action, then we would have the possibility of an asynchronous exception slipping in between before completing and calling after. So we can't restore there. We do restore inside the call to try, which is exactly what we wanted to be able to do for inner. Then we call after. We're still masked when we call after. That's a good thing. However, and this is where we get into some questionable territory, we're not actually uninterruptibly masked inside after. So it's entirely possible that after is going to use an interruptible action and get disrupted before it's able to complete its cleanup. That GitHub issue that I pointed everyone to earlier was part of that one. That's exactly what we were discussing in that issue. Should after always be run in an uninterruptible mask, or should it not be run in an uninterruptible mask? And that's that trade-off between exception safety and making sure we get things cleaned up and the possibility of deadlock. In the unleft.io package, and in safe exceptions as well, we've gone with the approach of using uninterruptible mask. Here we go ahead and pattern match on the result, and we rethrow the exception. This means that if it's an async exception, it's going to bubble up. It's going to be propagated, so we are not giving any way to recover from an asynchronous exception, so that's good. And if anyone forgets, I've written down all of these analyses in the solution slide. All right, this one is even more fun. So we're under racing reads. What is the output of this program? We've created a channel. We've stuck the numbers 1 through 10 in this channel. And now we're going to 5 times in a row try to read from the channel in 2 different threads. And we're going to print the result. So think about this. What would this output be? Well, you may think many different things. The answer is that this is timing dependent and implementation defined somewhat. It's non-deterministic. On my machine, I always got left values. So what ended up, and notice that the values 1 through 10, well, I skipped every other value. What ended up happening was the runtime system forked 2 threads. The first thread read the number 1, the second thread read the number 2. But the first thread then completed before the second thread completed. But after both of them read the value off of the channel. Therefore, the number 2 ended up getting dropped on the floor. Now, these timing issues are non-deterministic, so it's entirely possible that on someone else's machine or with a different workload going on, we would get a right value. It's possible we would get a left 2. It's possible that we would get left 1, left 2, left 3 in order without dropping anything. This is completely non-deterministic. So this usage of race in order to read from a channel like this is very dangerous. You can't do it. That might seem like a far-fetched example, so let's take something that seems a little bit more realistic. Let's say that I want to try to read from a channel. That channel might be empty, so I only want to wait around for 1 second to see if that channel has any values, and if it doesn't fill up with anything in 1 second, then I want to move on. So I use timeout. It seems like a perfectly logical thing for me to want to do. But I'm now going to simulate some kind of weird thread scheduling. Let's say that this read chan, after the read chan finished, but before we finished timeout, our thread got interrupted for 2 seconds, which may sound extreme, but it could happen. In this kind of situation, we will have read out a value from the channel, and then while we are currently being delayed, timeout is going to kick in and it's going to kill that thread, and we're going to end up getting a nothing value. We will simultaneously get a nothing, and we will drop a value on the floor. So we will be losing values from our channel. So how exactly can you actually read from a channel and use timeout? Well, you have to get a little bit more inventive. And this is the beginning of me pitching to you that you should really love the async package and the STM packages. Both of these packages are wonderful, and you can do many amazing things with them. So in this example, I'm now, instead of using a normal channel, I'm going to use a T-chan. I'm going to use a transactional chan from STM. I'm going to, just like before, I'm going to fill it up with the values 1 through 10. And now I'm going to use this register delay function, which is built into the runtime system, which is going to create a value. It's going to create a TVAR, a transactional variable that starts off in false. And after 1 second has passed, it's going to get switched, and it's going to say true. And now I'm going to have 2 different STM transactions. The first one is going to check if the delay is complete. And if the delay is complete, then it's going to return nothing. The second thing is going to try to read from the channel. And again, I'm going to simulate this weird timing with thread delay. Obviously, you shouldn't be doing unsafe things, but we're just trying to simulate something here. And then it's going to return the just value. In this case, there's no way for us to drop a value on the floor. One of these 2 things is going to succeed. One of them is going to fail. But we're either going to return the value out of the channel, or we're not going to pop it off the channel at all. So in this case, we're not going to have any values getting dropped on the floor. Okay. So I'm actually just looking at some of the QA. My advice versus monad-based control, I don't want to answer that one right now. The slides that I mentioned from Lambda World get into my concerns about monad-based control. I'm not going to cover it here. And what if you fork IO and cleanup, which will send goodbye, so current thread is killed. If you fork, okay, so that was from earlier. Sorry, I didn't see the question earlier. If you fork IO inside, in order to do the cleanup, the problem is that you then can't close the connection right away. And if you can't close the connection right away, you no longer have deterministic resource handling. So you have a situation where you're trying to clean up, but that thing could end up getting held around for an unknown amount of time. Maybe that's the right thing. Maybe that's the thing you actually want to do in that case. That would be an unusual situation, but that kind of thing could possibly happen. Okay. So forked threads. Caveat, like I just said, use the async library wherever you possibly can. When you're using the async library, there are some great functions concurrently in race. There are some sibling functions like map concurrently, replicate concurrently. There's a concurrently data type. Use all of those wherever you possibly can. If none of those work for you for some reason, then use the async data type and the functions that go along with it, async and with async. Only as a very last resort would I recommend these days using the fork.io function that I've mentioned so far and that we've used so far. It's good for low-level examples, but for practical code, prefer the async library. All of that said, let's get our hands dirty. And this is actually kind of connected to that question I was just answering. Let's say that I want to acquire a resource in the main thread, but in the child thread, I want to do the cleanup. So what I'm going to do is, now I'm just printing messages instead of actually acquiring a resource, but you can follow along and pretend like it's opening and closing a file. So we've gone ahead and we've acquired the resource. Now we're going to fork.io, start this new thread, and we're going to use finally. So finally should take care of all of the masking issues that we care about, right? And we're going to use it in the child thread, and we're going to use a thread delay just to pretend like we're doing something big. And finally, we're going to print out a message that says clean up in child thread. Immediately after forking this thread, we're going to kill the thread. Kill thread is a helper function which just uses throw2 under the surface. So it's a convenient way to kill a thread. And then we're going to exit the program. Now the output of this program is slightly time independent, but on my machine, this is the output. And you'll notice it never says use in child thread, and it never says clean up in child thread. The reason that's going on is that we fork this thread and we're about to call finally. And finally is going to go ahead and start off with some masking. However, before we're even able to start running finally, we call kill thread and we kill that thing. So it never gets a chance to install its masking. Well, we can try to do a little bit better. We can use uninterruptible mask inside our fork.io. That actually doesn't do anything at all. This is the exact same problem we had previously, because our thread is going to end up getting killed before uninterruptible mask gets called. We're not able to block the exceptions before they kill us. So that's not the right way to do it. Instead, we're going to run uninterruptible mask before we fork the thread. And what's going on here is we are able to inherit the masking state of the parent thread when we fork. So now we're actually going to get use in child thread to run. But there's still a problem. The problem is that we call kill thread, but kill thread isn't actually going to do anything anymore. Now that we're inside an uninterruptible state, the thread delay is never going to end up getting killed. So we're going to end up in a deadlock, or not necessarily a deadlock, but a very, very long lock. So this is almost correct. Instead of using uninterruptible mask, we're going to, under uninterruptible mask underscore, we're going to do uninterruptible mask and capture a restore function. And this restore function is now going to go ahead and allow us to interrupt our thread. And now this thing works. The problem here is very nuanced. I'm going to start off by showing you what the correct solution is, and then we'll see why. So instead of using the restore function provided by uninterruptible mask, we want to use this function called fork.io unmask. Actually, sorry, it's fork.io with unmask. That's a typo. And now instead of getting a restore function, we're going to get an unmask function. And the difference here comes down to what I'd said previously about wormholes, this concept of inheriting the masking state that already exists. If we were in a masked state, then that masked state is going to be the thing that gets restored by the restore function. But we actually want to guarantee that our child thread gets completely unmasked so that we're able to kill it. And if that seems a little esoteric, let's go ahead and demonstrate what this thing looks like. We've got three functions, foo, bar, and baz. Foo is going to use mask and restore, no threads, no nothing, and we're going to, after we've restored, get the masking state and then print out what it was. Bar is going to do the same thing, but it's going to do this action from inside a fork.io call. And then baz is going to do fork.io with unmask. And now instead of using the restore function, it's going to use the unmask function. We're going to run foo, bar, and baz 3 times each. One of them we're going to run unmasked. One of them we're going to run masked with interruptible actions, and one we're going to run uninterruptible masked. With both foo and bar, you see that even though we restored, well, we're just going to end up inheriting whatever masking state previously existed. But with baz, because we're using fork.io and the unmask value, we always end up in the unmasked state. And that's what we want in these forked threads. And that's why fork.io with unmask is so useful. That probably still seems a little bit esoteric. So now we're going to come back to the very beginning of this talk. We're going to be tying up here. Let's look at the bad race function. Bad race is going to go ahead and create an empty mvar for the result, whichever one of these things is going to die first. It's going to fork.io both of these threads, and it's going to put the values from these actions into the mvar, either as a left value or a right value. It's going to take the mvar to get the first result, and then it's going to kill both threads. One of the threads will already be dead, so the kill thread will be a no-op, but it will kill the other thread. And I can demonstrate that this thing at least somewhat works. If I use bad race on 2 actions, one that simply returns a unit value and the other which blocks indefinitely, and I print it, the result will be left unit, which is exactly what we wanted. Let's say that I masked and then I ran it. We're going to get the same result, which is fine because that's the way that masking works. We're going to be able to interrupt the thread delay. However, with our uninterruptible mask in place, this thread delay is now unkillable and we have totally broken our race function. There's no way for us to kill it anymore. And this is why the inheriting of the masked state doesn't make sense for forked threads. So we can fix that bug by using fork.io with unmask instead of using the restore function. And now this thing is actually going to work. There are other bugs in this example, which I'm not going to give any answers to right now. So I encourage everyone to go back and play with it and try to find some other bugs. That's that. There's another example which I actually was not able to come up with a demonstration that works today. Unsafe perform IO versus unsafe dupable perform IO gives a good example of why asynchronous exceptions need to work the way they do, but we're not going to be able to talk about that since I wasn't smart enough to figure something out. And we have a whole bunch of links at the end of this talk. I'm going to give you guys the link to the slide deck about lots of different things about async exceptions, exception handling in general, and recommended best practices. So that's all. If there are questions, comments, please follow up with us. I've given links to my Twitter account, FP Complete's Twitter account. And please, if anyone has any questions they want to ask in general about FP Complete, I've given our VP of Sales, Robert, has his email address there. So please, and again, like I'd mentioned at the very beginning of this talk, if you have feedback on the format, I know we were working out some bugs in my ability to do screen share and probably some audio issues. So look forward to hearing about how terrible it was for everybody. Great, so this was a lot of fun. And yeah, I'll stay on for another few minutes if anyone wants to ask some last questions. But I think we're at the end now. So thanks very much, everyone. Thanks for the feedback, everyone. Yeah, takeaway. Yeah, so takeaway, unleft IO, async, STM, those would be the things that I would tell you. In fact, if you look in the unleft IO package, it includes modules that it provide transformer-based wrappers around the async and the STM packages out of the box, because that's just the recommended best practice that I would say you should be using all the time. So tying those things together, you're going to bypass a whole bunch of problems. And if you go and you look at that talk that I gave about transformers from Lambda World, the reason for unleft IO versus monad-based control, I can get into it a little bit more here. Monad-based control ends up in a situation where you're able to lose some of the monadic state. Monad unleft IO is more conservative in what it allows as far as instances, and therefore there's no state to be lost, which is why I prefer it these days. Yeah, and for people who are asking, assuming we didn't have any bugs in the setup, we have done a recording, and hopefully this recording will work and we'll be able to publish it. Again, this is the first time we've done it. It seems to have worked in all of our tests, but if not, I guess I'll have to give the webinar again. Let's see. Certification courses. That's an interesting question. Actually, send an email to Robert and me about that. It's the kind of thing we've talked about in the past. We don't offer something like that right now, but it's something we'd be very open to considering. Okay, awesome. Thanks, everyone. I'm going to stop the recording at this point.